Hello student, this is the fifth lecture on the topic sequence and series. So we will start with a very important theorem. The statement of the theorem is if summation of an is convergent, then limit n tending to infinity an will be equal to 0, and hence you can say that the sequence is converging towards 0. So now we will prove this, and the proof is very simple. So in for proving this, you are given that summation of an converges. So you can write this. It converges means that you can find out its sum. So I write down the sum as equal to L. Now if you consider Sn, that is nth partial sum. So what you will get? This is your nth partial sum. And consider Sn minus 1, that is just you will add one term less than Sn. So this will be equal to this. Now if you subtract both this, that is nth partial sum and n minus 1th partial sum, so you will get an. It is easy to see. So now find out the limit of this. That will be equal to the limit of an. I am finding out the limit on both the side. So you can easily see that this will be equal to the limit of Sn, and the limit of Sn minus 1 will be equal to n L, because you are given this, that your series is converging towards the value L. So you have already seen that Sn will also converge towards this value, and similarly Sn minus 1 will also converge towards this value. So this will be equal to 0, which will be the limit of and this implies that your sequence will converge towards 0. So you have started with this, that you have a series that is convergent and it is converging towards the value L, and then following the step you have proved that the sequence is also going towards 0. There are some important points regarding the use of the theorem. First of all, do not misuse the theorem. The converse of the theorem is not true. That is, if you have a sequence that is converging to 0, then the series may or may not be convergent. So this is an important point to note, that the converse is not true. For example, if you consider the two series, this and another series is this. Now you will see eventually that this series is divergent. However, this series is convergent. But you will notice that for both the limit an tending to n tending to infinity, you are getting 0. Here also for limit this an is going to 0. So in both the cases you saw that the sequence, that is 1 by n, if I talk about the sequence, these both are tending towards 0. that is the limit of the sequence is 0, but the series, this series is divergent. However, this series is convergent. So an important note about the previous theorem is that the converse is not true. So keep this in mind. So here is our next theorem, which is called the nth term test for divergence. Now this theorem is like can be derived from the theorem from the previous theorem only by mathematics logic. You already know that if P implies Q, then minus Q implies minus P. That is, in the previous theorem we saw that if a summation of an converges, then the sequence will converge to 0. Now take the negative of q, that is if limit of an fails to exist or it is not equal to 0, that is the sequence is not converging, then we can say that the summation of an from n is equal to 1 to infinity also diverges. So this is called as a nth term test for divergence, that if the limit fails to exist or it is not equal to 0, then we can say that our series also diverges. So let us take some examples and see that if I ask you, tell me the convergence or divergence of this series. Now this theorem is very useful for proving the divergence of any series, that if you find limit n tending to infinity, n square is equal to infinity, that is not equal to 0, and it is not finite. Therefore by the above theorem you can say that this implies that summation of this an is divergent. Now if you see the another example, this is first, this is second. If you see another example, if I ask you whether this series will converge or diverge, so how can you say, like if you find out the limit of this, you will see that it is coming out to be 1, which is not equal to 0. Therefore you can write, therefore the series is divergent from nth term test for divergence. This is very good theorem for proving that the series is divergent, that if you get the limit an is not equal to 0 or it fails to exist, then you can say that the series is divergent. Let us take the last example for this theorem. So if you want to determine the convergence or divergence of the series, this. So for this you observe that the limit of n tending to infinity an is equal to what, minus 1 by 2, which is again not equal to 0. Therefore by nth term test for divergence, what can you say, the series this is divergent. So I hope that this theorem is clear, that whenever an is, that if you find the limit and if it is not going to 0, that is, if it is not equal to 0, then you can say that the series is divergent. So now I'd like to discuss a few properties which the series follows. So it says that we can add or delete finite numbers of terms from a series without altering its convergence or divergence. That means that you can add like finite numbers of term from the convergent or divergent series without changing its behavior. Like the convergent series will behave as a convergent only, and divergent series will behave as a divergent series only, even if you add or subtract any number of terms. But in the case of convergence, the sum of the series can change if you add or delete finite numbers of term. So let us see by an example. Like suppose if I have a series, this, now this series is convergent. You know, this is a convergent geometric series, and then I can also say that this this is from 4 is also convergent because I removed first, second and third term from this series. So whatever I obtain will be also a convergent series. However, the sum of this will be changed from the sum of this second one. So the sum will be like if you find the sum of this and if you subtract the first three terms, you will get the sum of the next series. Now similarly, if you consider another series, if I consider this diverges. Now if I add few more terms or if I delete few more terms, like if I started from 1, that means that I am adding few terms to this series, and if I delete, that is if I start from this, then also these both series will also diverge. So what is the moral over here? That no matters what, if we add a finite numbers of term or delete finite numbers of term, the behavior of the original series and the obtained series will be the same. Now I'll discuss about the reindexing or index shifting. This says that we can always reindex any series without altering its convergence, provided its term order have been preserved. That is, we can start a series at a different value for whatever the reason. I'll make it clear to you by an example. Like if you take a series, like take a series, take this series, or you take this series. All is like the same. Here you started from n is equal to 1. Here you started from n is equal to 3. Here you started from n is equal to 7. But all the series are equivalent. So you can always reindex the series without altering its convergence. Now consider another. If I ask you that start this series from
n is equal to 0. Now how can you do if I want to start the same series for n is equal to 0? How will you do that? Just you have to add, like I can write this series. I want to start it with 0. So what I have to do, I have to add this n plus 2. Now please check that you are getting the same series that I am getting right now, 2n plus 1. So if I open this, the first one, for from n is equal to 2 to infinity, if I open this, I will get this. And if I open up the second one, which I started from n is equal to 0, so what will you get? You will get the same series. So it says that you can reindex the series from wherever you want and whatever the reason for you which you want to reindex. It's your choice, but for every series you can do that.
Now we will see how we can combine two convergent series. So if we have a two convergent series, then we can add them, subtract them term by term, and multiply them by a constant to make a new convergent series. So this is a theorem which says that suppose that you have a series which converges to A. That is, you can find its sum and it is equal to A, and another convergent series which is converging to B. Then if you add the two series, it will converge to A plus B. If you subtract, it will converge to A minus B, and if you multiply it with a constant term, it will become this. Okay, so it is important to have this remarks that every non-zero constant multiple of a divergent series is divergent. That is, if this series is divergent, then if you multiply this with a constant, then this will also be a divergent series. Now, the second remark is if a series diverges and another series converges, then if you add or subtract both the series, then it will always diverge. That is, if one of the series is divergent and if you add or subtract, then it is also divergent. And the third is that if you have two series and these two series are divergent, then it is not necessary that if you add those two series, then it will also diverge. So I feel that these two remarks are okay, but this for this third, you can see by an example. Like I'll give you an example for this third remark. Now suppose that you have two series. I write to an that is equal to 1 plus 1 plus 1, and you have another series which is equal to, and so on. So now you can easily check that if you take out the limit an n tending to infinity, you are getting 1, and limit n tending to infinity bn is equal to minus 1. Now since an is not tending towards 0, this implies that summation of an is divergent. Similarly, you can see that bn is not tending towards 0, therefore summation of bn is also divergent. by nth term test for divergence. Now see that if you will add these two series, what you are getting, so this will be equal to 0. Obviously you can find out the sum and this will be equal to 0. This implies that summation of an plus bn is convergent. So you have seen that you took two series that are divergent and you proved that the sum of the two divergent series need not be divergent, they can converge also. Now we will take a example. Let's see. So this is our next example, that you have a series this. Now you can write this series as, so this will be again equal to, now this is my convergent G series. Why it is convergent? Because you have already proved that the geometric series are convergent if mod of R is less than 1. So obviously here R is this, and this is also convergent G series with R is equal to 1 by 3, which is again less than 1. Therefore you have already seen the theorem for combining series. Therefore the entire series, this one, will be convergent because these two are convergent. So if I subtract the convergent series, I'll also get a convergent series. So this is also convergent. And what will be the sum? And its sum will be equal to, you already know, a1 minus r. So I'll write its a is 2 by 3 for first series, 1 minus 2 by 3 minus 1 by 3, 1 minus, so this will be equal to 3 by 2. So you have finally proved that this is a convergent series with the sum 3 by 2. Question on combining the series. This, suppose that you have a series that is equal to, I called it as summation of a. So now you want to find out the convergence and divergence for this entire series. So you can write this series like this. Now obviously you know that this is a convergent G series with R is equal to half. Now what about this? If you see, this is, now this will be divergent series. So by the theorem of combining of series, you see that the first one is, this one is convergent, and this one is convergent, and what about this one? This one is divergent. So if one series is convergent and one is divergent, so what we can conclude that therefore the summation of an is divergent. I hope this is clear. So now I'll request you to go through this book, Analytic Geometry by Thomas and Finney, ninth edition, and do exercise 8.3. And this is given in section 8.3. And after reading that section, do exercise 8.3. Thank you.